Okay, I think we're recording. Hello, my name is Sergio Garcia. This is my chapter 7 video for the test, part 1. This will be similar to chapter 6 and every other video that I've done before this. This is essentially going to be a brief overview of the chapter, going over essentially a lot of the equations and basic knowledge that'll be important when going through the chapter or just like taking the test on it. So I think that I will just start there. The focal point of chapter 7, similar to chapter 6, how chapter 6 is focal point is all about work. The focal point about chapter 7 is gravitational potential energy, right? So how do we calculate gravitational potential energy? Well, it's split up like this. So U-grav, which is our sort of our symbol for gravitational potential energy, is equal to the mass of an object times its gravity times the constant of gravity times y, where y is the particle. So y in this situation is something that increases as an object grows higher in the vertical direction. And in the same vein, when the object goes in the vertical direction, the gravity will go in the negative direction, right? So it's just something that you can think about there. If an object is raised, the y will increase and the gravity will be negative. So that's like the general function that's the basis of chapter 7. It's essentially just understanding how we can calculate gravitational potential energy. Nextly, we have a law or equation that helps us understand the balance of mechanical energy. So the law of conservation of mechanical energy essentially states that the kinetic energy and potential energy of an object is always the same, or will always add up to the same thing. So what this equation says when it says K1 plus U grav 1 is equal to K2 plus U grav 2, it's essentially saying that the kinetic energy from one either position in time or position in relative distance, plus the gravitational potential energy at that same position is equal to the kinetic energy of a different position in time, plus the potential gravity at the second point in time. So it's saying that no matter what the point in time is, even if the kinetic energies are different, even if the potential energies are different, the sum of those two things will always equate to the same number. So the best way I could explain that, if I could draw right quickly. So this is just a random example I'm doing off my head. So if you had this kinetic energy being 20 and this U grav equaling to 100, right? The sum of those two is going to be equal to 120. And what the law of conservation of mechanical energy tells us is if that K2 is equal to, I don't know, 70, right? K2 is equal to 70, then U grav would be equal to 50 because the sum of their totals would have to be equal. And since this equals 120 and this equals 120, then they both equal 120, and the conservation of mechanical energy in the situation is conserved. That is a rule of physics that cannot be changed. So it's important that you can understand that, because that'll help you understand, like, let's say you're given the potential gravity at a point, but not the kinetic energy. You can find the sum of a different point if you have these two, and then find this last unknown. Finally, well, not finally, well, I'm getting ahead of myself. Nextly, we have work and energy along a curved path. So we saw something similar with, I believe it was kinetic energy in last chapter. So it's saying that the work along this path is equal to your mass times gravity of particle y1 minus your mass times gravity of particle y2, or your U grav 1 minus your U grav 2, and that'll equal to your work of gravitational, of just gravitational potential energy, which I think makes sense. This is what you'll run into when you're looking at a graph. Important things that could be said here is just knowing that, because you can manipulate this to have it so that work of gravitational potential energy plus U grav potential energy is equal to U grav 1 potential energy. So there's manipulations that you can use here. If you have two of these, you can find the third. This is stuff we've seen before with manipulating equations. Nextly, we have elastic potential energy. So this is, let me get a, is this the right purple? I hope so. No, it's not. Let me fix that E, because that's what that is right there. This is potential energy. This is elastic, right? And it says that is equal to 1/2 of your kinetic energy in the x direction squared. This is also relatively simple. It's just 1/2 x squared. There's not a lot of manipulation you can do here, but essentially when you find elastic potential energy, you take your kinetic energy in the x direction, so going left to right, and you multiply, and you you square that and then divide it by half. Nextly, we have the law of conservation of energy. This is saying that the addition of all potential energy and kinetic energy, any of that, essentially when you add kinetic energy and potential energy, the final sum amount will always be 0. And that's to say that kinetic energy, when added with its potential energy, they will always sum to 0 because one will be negative, one will be positive, and the difference between the two will always be 0 because they just always cancel out. The way that works essentially in like a broader sense is that energy cannot be created or destroyed. And since everything has a set amount of potential energy that's converted to kinetic during an action, or kinetic that restores into potential when an action is finished, that means that no matter what, there will never be an overproduction of energy. Energy exists and is transferred between two forms, being kinetic and potential. So that means that their sum amount when added up together will always be 0. Now, conservative energy using potential energy. This formula is essentially just saying that the force x of x is equal to the negative du times x dx. This is like a derivative of things that we kind of understand from law of conservation of energy. Only difference is it's using the derivative of potential energy to find the force created by the conservative energy. And that's essentially the brunt of chapter 7. It's a bit smaller than chapter 6. There's more to discuss in the last chapter, but that does not mean that what we learn here is not complex. So yes, thank you for tuning in. There's not anything I have left to say. I'm checking my notes right now. No, it seems good. So thank you for your time, and I hope you have a good day.